So we've hit all the topics in this section that we need to hit. Alkyl halide substitution elimination. It can do SN1, SN2, E1, E2. Alcohols substitution elimination. They can do SN1, SN2, E1, and E2. Ether substitution, no elimination. They can only do SN1, SN2. Epoxide substitution only by SN2. Sulfonate esters can do SN1, SN2, E1, E2. Sulfur-containing compounds like sulfides and sulfonium salts, darn good at SN2, doing SN2 and being SN2 upon, and quaternary ammonium hydroxides, E2 and E2 only. That was a quick recap. Should I write some of it down for us to follow along? Maybe. We'll start out with alcohols. Alcohols. Well, if you have a secondary or tertiary alcohol, allylic or benzylic alcohol, those like to make carbocations. That means SN1 or E1. If you have a primary or methyl alcohols, those are not crowded substrates. Those do 2-paths more often. There are exceptions. Hold on. The bigger deal, the slightly bigger deal, the different deal, maybe let's say it that way, the different deal with alcohols and alkyl halides is it depends more on what type of reagent you do as to whether you do substitution or elimination. So let's look at reagents. If we add things like HCl with zinc, or HBr, or HI, if we add things like acids like those are acidic conditions. That means you're going to do substitution. You'll do SN1 if it's secondary, tertiary, allylic, benzylic. You'll do SN2 if it's primary or methyl with those reagents. If you add reagents like Sokol with pyridine, Pieber with pyridine, Pickel with pyridine, those are basic conditions. That changes the way things work. You do substitution via SN2 only. That says via. SN2 only. These do SN1 and SN2 depending on the substrate you've got. But Sokol, Pieber, and Pickel do substitution via SN2 only. Acidic versus basic, you change the way that thing works a bit. Sokol and Pieber and Pickel do not work on tertiary alcohols. Beware. Does not work on tertiary alcohols. We got two more things to write down here, and I'm afraid I'm not going to be able to fit them. If you add reagents like H2SO4, H3PO4, or BS3, these are often heated, but those are acidic conditions. But those acids have big, bulky conjugate bases, and those conjugate bases have distributed electrons, delocalized electrons. We're going to do elimination. Totally not legible. Elimination down there. Elimination almost always will go E1. But if it's a primary alcohol, you're not going to eliminate a methyl alcohol because you got to have two carbons to do elimination, right? Yeah. If it's a primary alcohol, it can do E2, but that's really a special case. Remember, remind yourselves, go back to that example. We did a primary alcohol via E2, but it ended up making a carbocation anyway because we were refluxing, heating for a long time in acid anyway. So, yeah, it can do E2 if you're primary, but mostly we're going to see E1 with these guys. So we'll make some space up here, I guess. Alcohols can be substituted if you add things like HCl with zinc, HBr, HI. Alcohols can be substituted with things like Sokol and pyridine, PBR and pyridine, Picol and pyridine. That's two separate acidic and basic conditions. They do slightly different mechanisms depending on acidic or basic. Alcohols can be eliminated if you add things like H2SO4, H3PO4. That's acidic conditions. They're going to do mostly E1 megacarbocation kind of thing under acidic conditions. But alcohols, if you add something like Pacol with pyridine, that's basic. And under basic conditions, we are not ever, never, ever, never, ever going to make a carbocation. Never, ever, ever. Never, 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 never. So we're going to do elimination, but E2 only. It doesn't matter if it's primary, secondary, or tertiary. If you're adding Pacol with pyridine, you are not going to make a carbocation. I think that's a pretty reasonable summary of substitution and eliminations of alcohols, but alcohols can also be oxidized. So let's swipe this slate clean and talk about alcohol oxidations. Alcohols can be substituted to make alkyl halides. Alcohols can be eliminated to make alkenes. Alcohols can be oxidized. Oxidation, let's say that. Oxidation of alcohols can make ketones, aldehydes, and carboxylic acids. Those are the three types of functional groups you could create when you, that was ugly and I tried again and then it all disappeared. Aldehydes. Those are the three types of functional groups you can create when you oxidize an alcohol. Okay, we need to know if our oxidizing agents are strong or weak. I really want you to give me some examples of strong and weak oxidizing agents. I'll pause for you to think of them. You should pause too for you to think of them. You got them? Y'all ready? Strong oxidizing agents, in general, are anything with chromium and acid. Some specific examples are CrO3 with acid, Na2CR2O7 with acid, H2CrO4, that is chromic acid. Na2CR2O7 could also be K2CR2O7, sodium dichromate, potassium dichromate, it doesn't matter. Chromium with acid are strong oxidizing agents. What do strong oxidizing agents do? They turn secondary alcohols into ketones. And they turn primary alcohols into carboxylic acids. You don't have room to write the whole word. They turn tertiary alcohols into nothing. No reaction with strong oxidizing agent and a tertiary alcohol. They would turn a methyl alcohol into carbon dioxide. Well, yeah, okay. Weak oxidizing agents. That's PCC. That's chromium with base. It's officially C5H5NH+. Cl, or actually you'll see it more often, CrO3Cl-. PCC, pyridinium chlorochromate. You'll also have bleach as the weak oxidizing agent. That's sodium hypochlorite and acetic acid. You'll also see the Swern oxidation as a weak oxidizing agent. That's DMSO and oxalyl chloride. Yep. What's different in strong and weak? Weak turns tertiary alcohols into nothing. There's no hydrogen there to be oxidized, no reaction. Turns secondary alcohols into ketones, just the same. Turns primary alcohols into aldehydes. It does a weak aldehydes. turns primary alcohol into aldehydes because the weak oxidizing agent, it just does a mild oxidation, one layer of oxidation. Yeah. We covered alcohols first because they're the most complex. They have the most things that you can do. You can do substitution to make alkyl halides. You can do elimination to make alkenes. You can do oxidations to make carbonyls, and all of those are carbonyls. You can do, alcohols can act as nucleophiles to make other groups. Alcohols as nucleophiles. We saw 2 functional groups get made with alcohols as nucleophiles. We saw esters be made, as in organic esters, and we saw inorganic esters be made. In order to make an ester, the reagents were alcohol. We saw 2 ways, plus carboxylic acid, plus extra acid. Alcohol plus carboxylic acid plus extra acid made an ester. Alcohol plus acid chloride plus pyridine made an ester. And acid chloride is kind of like a carboxylic acid, but a Cl instead of an OH over there. We drew the mechanism for those reactions, but we do not have to remember that mechanism yet. We won't have to remember that mechanism until Unit 3. Those previous, I should have said so before I erased it all. All those other reactions, we do need to know the mechanism for it if we drew it. Substitutions to make alkyl halides? Yes. Substitutions, eliminations of alcohols to make alkenes? Yes. Oxidations of alcohols to make carbonyls? Yes, except we did not draw any of the chromium mechanisms. We don't have to know those. We need to know bleach and Swern. But other than that, all the chromiums, nah. We drew these, but we don't have to know them yet. Okay, now, back to where we were. We also made inorganic esters. We made sulfonate esters. We saw how phosphate esters react as well, but we didn't actually draw how a phosphate ester is made. So we did draw how a sulfonate ester is made. Sulfonate esters are alcohol plus a sulfonyl chloride. We saw tosyl and mesyl and triple chloride react to make sulfonate esters. We do need to know the mechanism of how sulfonate esters are made. That's all the reactions that we talked about with alcohol, substitution and elimination-wise. But since we're ending on sulfonate esters, I think it makes good sense to start our next thing as sulfonate esters, because those are another functional group that we need to know how a sulfonate ester reacts. It's real easy to write a summary down here. They follow the flow chart. Follow the flow chart. Yeah. What flow chart? The one for alkyl halides that says methyl SN2. Primary SN2, almost exclusively. Secondary anions, yes. Strong base, no. SN2. Secondary anions, yes. Strong base, yes. E2. Secondary anions, no. SN1 and E1. Tertiary anions, yes. E2. Anions, no. SN1, E1. That flow chart, yeah? Sulfonate esters do all the same things that alkyl halides do. The alkyl halide flow chart. Yeah. Alcohols do not follow the flow chart. Don't do that. Sulfonate esters and alkyl halides follow that flow chart. All right. We talked about alcohols and sulfonate esters. Then we moved on to ethers. Again, I say we talked about alcohols first because they do the most things. Ethers do substitution only. They do not do elimination. The only types of reagents that ethers react with are things like HCl, HBr, and HI. They're often heated at the same time as well, but that's the only thing they react with. They don't react with H2SO4 or anything of the like. Only alkyl halides. Only acid halides like those. So we said if it's methyl primary or secondary, SN2. If it's tertiary, allylic, benzylic, SN1. SN1. And I pointed out when we talked about it then, and I will point it out again now, secondary is different. Alcohols that are secondary make carbocations. Ethers that are secondary do SN2. The other thing we talked about with ethers is when you have an SN1 versus SN1 disagreement, make better carbocation. That means make benzylic over tertiary because a benzylic carbocation is more stable than a tertiary carbocation. When you have an SN1 versus SN2 disagreement, make a carbocation. That means you're going to do SN1, not SN2. When you have an SN2 disagreement, attack least crowded. As ethers. But there's a special category of ethers called epoxides. Excuse me. Epoxides. They do substitution only, but furthermore, they do SN2 only. The big deals about epoxides were if you have acidic conditions, versus non-acidic conditions. You do different things. In acidic conditions, pronate first, you get a heteroatom with a plus charge. You're worried about carbocation character. Attack most substituted side. In non-acidic conditions, basic conditions, neutral conditions, non-acidic conditions, you're worried about accessibility. Attack least substituted side. Substituted, yeah, side. So ethers do substitution only, but epoxides go even further and do SN2 only. You got to worry about inversion and all that stuff, but yeah, epoxides do SN2 only. You got to know if it's acidic conditions or not acidic conditions. One little thing that I think is worth pointing out here is that Grignard reagents. What the heck are Grignard reagents? Grignard reagents are great. Oh boy. Grignard reagents are great at attacking epoxides and busting open epoxides. Note, Grignard reagents have very distinct steps. Number one, add the Grignard, whatever that Grignard is. And number two, add acid. Lots of students see this acid and say, ooh, this is acidic conditions. No way. This Grignard is added to your epoxide first, and the Grignard itself is a crazy strong base. After the Grignard does its reaction with the epoxide, that's when the acid comes into play. The acid and epoxide are never in contact because the Grignard destroys the epoxide before the acid is ever even added to your flask. So Grignard reagents are strong bases. They are definitely non-acidic conditions. Beware, even though there's acid as the second step, it's the second step. It doesn't count. We're coming in for the home stretch. We've talked alcohols. We've talked ethers. We've talked sulfonate esters. We've talked epoxides. Up next was sulfur-containing compounds. They almost exclusively do SN2. It's hard to say that it is exclusively SN2 because they could officially do something else, but almost always sulfur-containing compounds do SN2. They're good at doing SN2 reactions, acting as a nucleophile. They're good at being SN2'd upon if you have something like a sulfonium, sulfur with a positive thing. SN2 pretty exclusively when you have a sulfur-containing thing. And the last thing we talked about was quaternary ammonium hydroxide. They did E2 and E2 only. You got Hoffman elimination. We started off with a bang that was going to seem really confusing because alcohols can do so many things. But then we hit several other functional groups that don't do lots of things. So I think it's a pretty good wrap-up. I like it. Let's see how to use that recap, that knowledge in a few problems. Starting with R, 1-deutero, 1-propanol. 1-propanol, 1-deutero, and it should be R. That means the deuterium needs to be dashed in order to be R. How could you prepare S, 1-deutero, 1-propanol? Oh, well, it's the same thing, just wedged. How do you change the stereocenter but keep the functional group the same? Well, you need your terrible, horrible, no good, very bad leaving group to be turned into a better one. One example of turning that thing into a better one is turning it into a sulfonate ester. Sulfonate esters do not attack that carbon. So if you add MSCl and pyridine, you get the same stereocenter that you had previously, dashed D, and you get a good leaving group now connected to your, what was your alcohol. Then you can do, that the primary sulfonate ester, follow the flowchart, primary says SN2. So let's add something that's going to do a good SN2. We'll get inversion. Are there other options? Sure. This is one of the options I could think of, but could you come up with something else? Absolutely. I like this one, though. What about if we tried to start with the same R, 1-deutero, 1-propanol, and we are trying to make R, 1-deutero, 1-methoxypropane. There's our methoxy. It needs to be R. 1, 2, 3, 4. Yep, that's R. So this one, you could do a couple of things. One of the things you can do is deprotonate that alcohol. I did not mean to make that NaOH. I like NaH better. NaOH is not so great at deprotonating alcohols and favoring products at equilibrium. NaH will deprotonate that alcohol to make it an O-. That does not mess with that stereocenter at all because it's just an acid-base reaction. And then I can add like methyl bromide, methyl iodide, SN2. That's one way. Is that the only way? Well, heck no, of course not. I could also, going up north, I could also do something like HBr. HBr to that primary alcohol is going to do SN2. SN2 makes it a Br and a deuterium that's wedged. Okay. Then I have a primary alkyl halide. Primary alkyl halides say SN2. So if I do another SN2, this time with like Naomi, I can do SN2 on that halogen to yield this methoxide. It's a double SN2, so it's a double inversion. It looks like retention overall because this D is dashed, this D is dashed, but it's really a double inversion that leads to something that looks like retention. Either of these syntheses are totally valid. This purple one is much more related to stuff we talked about last semester. The blue one is much more related to what we talked about this semester. I don't care which one you present. You get good credit for both options because you got to know both options because organic is cumulative and you got to know last semester and this semester and, whew, oh joy. So this is just a little something taken out of your textbook that says there are a couple of ways you can think of activating an alcohol. We've actually just used these in practice. Maybe I should have talked about this before we did that synthesis, but oh well. If I add PBr and pyridine, that's going to do SN2 on my alcohol. So I end up with my center getting inverted. I've got a Br on a wedge and my hydrogen on a dash. PBr does SN2 inversion, shown like that. Then I have a secondary alkyl halide and I add this methoxide. Secondary alkyl halides with methoxide, it might do some elimination, but let's do another SN2 because that's what the textbook is wanting you to do. So we got methoxide doing an SN2 on that bromine. And we end up inverting yet again to have methoxide, that's an oxygen, methoxide pointed backwards and the hydrogen pointed forward. So the point of the question in the textbook is you start out with, if R is priority number 2, you start out with S stereochemistry, and in the end you end up with S stereochemistry. How is that possible when you did SN2? The point is you do 2 SN2 reactions in order to get what looks like retention of configuration. And then, in the next example, tosyl chloride and pyridine does not do SN2. Tosyl chloride and pyridine does an SN2 on the sulfur, not the carbon. So your stereocenter stays the same. And then you have a secondary tosyl, and you do an SN2 with methoxide. So that's when your stereocenter gets inverted. We got hydrogen back there and methoxide pointed that way. And their point is we start out with S and we end up with R in this example. Why is that different? In the top example, you went through 2 SN2s, double inversion. In the bottom example, you went through 1 SN2, so only 1 inversion. That's why you get R in the bottom product and S in the top product. Yeah. Yeah. Propose a mechanism. All right. I have an alcohol, and alcohols can be substituted. Alcohols can be eliminated. Alcohols can be oxidized. Alcohols can act as nucleophiles. We can do a lot of things. It's a primary alcohol that I'm reacting, and this is acid. Primary alcohols and acid, we've seen those do substitution and elimination, depending on what kind of acid it is. Acids like this do elimination. And my product actually shows me that I'm going to do elimination. So am I doing E1 or E2? Well, it's a primary alcohol. I'm not going to make a carbocation that's primary. So off to the races I go, getting started on a mechanism. Make my alcohol a better leaving group, like this. And then I do an E2 elimination because it's a primary alcohol. I shall not make a primary carbocation. So I'm going to take a beta hydrogen alpha, beta, beta hydrogen from here. Dump in electrons, kick out water, and I get alkene. Ta-da! Oh, no ta-da. What? This product that I just made is not that product. What's the difference in these? Alkenes, when they're refluxing, sitting around, heating an acid, that's going to equilibrate to make something more stable if possible. So we've got sulfuric acid around. Let's protonate that alkene like this to make a carbocation. What? I thought you said we weren't making a carbocation. We're not making a primary carbocation. When we protonate, we make that carbocation that's tertiary. That tertiary carbocation can undergo another elimination, a Zaitsev elimination. Beta here. We've got alpha. That's the carbocation. Beta, beta, beta. Zaitsev elimination means take a hydrogen from the beta with the fewest, and we get the product that we were requested to draw a mechanism for. Yeah? Primary alcohol dehydrations are weird little things. They make unexpected products. They almost look like they go through a primary carbocation, but they don't. They go through an E2 to make an initial alkene, and that initial alkene often gets protonated to make a carbocation that's more stable than a primary carbocation, and that undergoes a subsequent elimination. Yeah? Yeah. All right. How about some epoxides? We haven't done enough epoxide examples. Is this acid, is this base? Because that's my major concern when I talk about epoxides. This is basic conditions, aka non-acidic conditions. This is an amine. It's a non-acidic condition. In fact, there's one thing you know about amines, and it's that they are bases. So both of these are under basic conditions. What does that mean? It means attack the least substituted side, like so. There's the product according to our book. Attack the least substituted side. You get an O minus. O minus goes through acid workup, some sort of proton source, solvent, something, some sort of proton source to give you the neutral alcohol. This amine is my nucleophile, and I attack the least substituted side, like so, to give me this product. This product has nitrogen with a plus and an oxygen with a minus. We need to neutralize that thing. We don't have to add solvent or any other proton source. It can neutralize intramolecularly like that, or through other molecules. They all become neutral to give me this product. Yeah? Epoxide, you got to know if it's acidic or basic conditions, acidic or non-acidic conditions. One more. We can make cis-diols, but can we make trans-diols? First, we might need a reminder how to make cis-diols. How do you make cis-diols? Osmium tetroxide and peroxide added to an alkene. Cis-diol, OH, it's a vicinal diol, that's cis. If I add Br2 and water to an alkene, I get a halohydrin. That's those two compounds, those two enantiomers. Add NaH to those enantiomers, and what do I get? I get an O minus. NaH is a base. I'm doing an acid base. O minus. That O minus, and then does an intramolecular SN2. Like that, to give me this little epoxide down in the corner. Little epoxide down in the corner. What if I add sodium hydroxide? This should probably also have water as a solvent. Sodium hydroxide and water, it's basic conditions, aka non-acidic conditions. Bust open that epoxide on the least substituted side, but it doesn't really matter here because it's equally substituted. We'll make an O minus. O minus. OH. And then water will neutralize that thing. And we end up with this vicinal diol. But it's a trans vicinal diol, not a cis vicinal diol. Why do we remind you of how to make vicinal diols these two ways? Because vicinal diols do very weird dehydration. Vicinal diols always rearrange. You remember that? Vicinal diols always rearrange in such a way that you get a carbocation that has resonance and you end up with a carbonyl compound. Maybe you followed along with all those words. There are videos to rewatch if you didn't. All right, I'm done.